Hey everybody, and welcome back to the channel. First of all, thank you for 30,000 subscribers. It means a lot to me. Would not be here without all of your hard work watching these videos, so again, thank you a lot. Second of all, I am getting ever closer to the follower count of this one influencer girl who rejected me a couple years back. So my revenge plot is almost done. I can finally text her and tell her how much better I am than her. But we still have to keep grinding for a few more years to get there. So let's keep going. Today we'll be talking about distributed locking. Okay, cool. So I'm going to try and get through this one relatively quickly as I have a Knicks playoff game to watch, and it is a big season that we've got here. So first off, the main thing to note with this video is that it's mostly going to be synthesis. I'm not really going to be introducing any new concepts to the 2.0 series in this video. I'm just going to be trying to tie a lot of them together, and we're going to be doing so in terms of building out a distributed lock. So what is a distributed lock? For those of you who do not know, let's imagine that we have node 1 over here. So that's one server. We've got node 2 over here. What we would want to use a distributed lock for is to basically avoid them both writing to some third-party resource at the same time and corrupting it, right? So for example, if we have some document in S3 and I can basically read that document and write an extra line to it, if we're both writing that extra line at the same time, maybe S3 doesn't have the proper locking protection that we need, we could corrupt that file. We want to make sure that we have mutual exclusivity, and so what we do is we make this other service, which is a lock, such that only one node can grab it at a time, the other one is rejected, and then the other one is eventually going to have to come back when that lock is released. Let's go ahead and formalize that. So basically we want to build some lock that multiple different nodes, so literally different physical computers, can use to ensure mutual exclusion. And the idea here is that we want it to be functional in the event of hardware failures. It's not enough for me to just have a single node and be like, okay, you guys can reach out to this thing via a REST endpoint and whoever gets there first wins. We need this thing to be fault tolerant like any other system that we're planning on building. The reason for that is that a lot of our servers are going to potentially be relying on this. For a particular lock, we can have up to 100 nodes that may be trying to grab it at the same time. Now, admittedly, this capacity estimate is not really going to come into play too much during the course of this video, but more from an abstract perspective, we want to talk about how to make sure that we're not having all 100 of those computers competing with one another at the same time and causing a ton of load on that distributed lock. Cool. So the first thing that we're going to be talking about is consistency. There's going to be a lot of database theory in this video, so it should be a nice throwback to all of these concept videos. So whatever we do need to build has to be strongly consistent. It has to. The reason I say that is this, right? Let's say we've got guy over here trying to grab the lock, and our lock looks something like this, where we've got a leader and a follower. So in the first step, we grab our lock, we get our lock in step 2, and then in step 3, guy on the right also wants this lock, goes ahead and does that from the follower, right? So he says, ooh, follower, has anyone grabbed the lock? Follower says, no, go ahead. And then, in fact, you can have it as well. So now this guy thinks he has the lock because he saw that no one else grabbed it. And so because this is happening asynchronously, right, this replication step here is actually happening in step 5, it is possible now that both of these guys think that they have the lock. They're both going to write to S3, and now we have a problem in our hands. So again, anything involving stale reads is not going to do it for us. We need linearizable reads, and we need to be able to avoid two people writing to the same service at the same time. Cool, so now that we've covered that, it also happens to be the case that simply avoiding stale reads is not enough, right? So let's imagine this guy right here, this middle node is our distributed lock. We've got both of these clients who want to be grabbing the distributed lock. And here is the event of steps that may happen. In step 1, the guy on the left is going to ask for the distributed lock, and it gets granted it in step 2. In step 3, it's going to go through a long garbage collection process. Now, if you're familiar with the Java language, you might know that depending on the garbage implementation algorithm that you're using, or the garbage collection algorithm that you're using, it can actually literally stop everything in that program. It could be a stop the world process pause. And so this guy might look to be completely dead for a few seconds at a time, so much so that in step 4, our distributed lock says, you know what, I think this node is dead, I have to expire this lock. Now you might say to yourself, well, this could be solved if we just never expired locks unless the client said to unlock it. However, that's infeasible, right? This guy could go down, I might take a hammer to it or nuke it or something like that. And so at the end of the day, we do eventually want to have a TTL on all of these grabs of the lock. Cool, so this guy expires and all of a sudden the distributed lock says, hey, you can grab me again. So client number 2 comes along and does the same exact thing in steps 5 and 6. In step 7, Client number 2 is going to write to S3, and then in step 8, client number 1 finishes its garbage collection, says, nothing's changed on my end, I still have the lock, writes to S3. That would be bad. So we can't be having that. So what do? We implement something known as fencing tokens. So in a fencing token, what we basically do is we assign every single grab of the lock some sort of increasing sequence number, right? So let's just do monotonically increasing for now, such that let's say, client 1 gets the fencing token 15. Since client 2 is the next guy to grab the lock, he will have the fencing token 16. And when he writes to S3, he'll tell S3, hey, I'm writing with fencing token 16. What this does is it ensures us that if client 1 comes back along and tries to write at the same time as fencing token 16, we're going to say, ooh, you know what? This token is smaller than a token that I've seen before. We're not going to accept your write. You're just going to have to let this one go. And then all of a sudden, we're good to go, right? So we're never going to basically be moving backwards in time. We shouldn't have previous grabbers of the lock writing to our service after they've been given that approval and, having it revoked as well. Cool. The next thing that we're going to be talking about is single leader replication. Could we build out a distributed lock using single leader asynchronous replication? Well, as I mentioned, pretty much right off the bat, no, because of eventual consistency. But let's cover another problem that we can deal with, because in this one, you might say, oh, well, we're going to have eventual consistency reading from the replica. However, what if we both wrote to and read from the leader exclusively? So the question is, does this work? In my case, I'm going to say no. So like I mentioned, if we want to build this thing in a fault-tolerant manner, we do ultimately need replicas, right? It's not enough to just have one node. We're going to have to store this data in multiple places because I can take a hammer to that leader. So let's look at the following scenario. In step 1, the guy on the left is grabbing the lock, gets assigned a fencing token of 15. In step 3, the leader goes down. Oh no, but this is asynchronous replication. So we got unlucky with our timing, and all of a sudden the process of me telling the follower that the guy on the left has the lock doesn't actually go through. Now all of a sudden we have a bad failover condition. So when we fail over, right, which is basically promoting a follower to the next leader, that's going to happen in step 4 over here, our follower becomes the leader, we're now going to grab the lock on this follower node, which was never aware of the original lock grab. And so this guy is now going to say, hey buddy, you've got a fencing token of 15, right? So now both of these guys have the same exact fencing token, and both of them can go to S3 with the same fencing token, and S3 thinks that all of those writes are coming from the same place, and as a result is going to get corrupted, right? Because now they're writing to that same file, and that is bad. So basically what this tells us is that a single leader replication, even when completely writing to and reading from the leader, is still not going to work, because in the failover scenario, we can lose writes, right? This is not perfect. It is not completely strongly consistent, so we're susceptible to failures. Now, are there cases where this might be sufficient for your service? I'm sure there are, but the point is we want to build something that is not susceptible to failure, whereas the above system was. Cool, another option is that you do the same exact thing. However, all of a sudden now instead of asynchronously replicating, you replicate synchronously. Obviously, this isn't going to work, right? So if I'm this guy on the left over here, and for me to grab the lock, I also have to write to this guy over here, and this guy over here, and then that comes back to this guy over here, and then that goes back to the client. That doesn't work because now all of a sudden if one of these guys breaks, no writes can be propagated because we're basically waiting on all of them to get propagated around the system before we complete a write. So in the event that any node goes down, everything stops, no more writes can be done, so we have no fault tolerance. So synchronous replication, as per usual, is not going to work very well. Now let's start getting into other forms of replication. The one that I'm going to talk about here is quorum consistency. So the reason that I talk about it is because there is a pretty common misconception that when you use quorums, like in Cassandra, they are strongly consistent. Now, is this actually true? I'm going to go ahead and say no. So let's talk about why. As a quick reminder, what are quorums? Let's say we're using some type of database where all of the nodes can be written to, right? Every single node is considered a leader. And let's imagine that there are n of them. In the example below, n is equal to 3. So if I'm a client and I write to W nodes, and then every single time I read from R nodes, and W plus R is greater than N, I can actually guarantee that whatever I write will be seen by any reader, right? So let's do an example of that quickly. Here's my writer over here. In this scenario, W is equal to 2, meaning that I have to write to 2 nodes at once for my write to be considered successful on the client. So I write to both of these guys, and I hear acknowledgments from both of these guys, and so the client says, okay, my write was successful. Here's another client over here reading from 2 nodes because R is also equal to 2. And so you know that in a cluster of size 3, if I write to 2 nodes and then I read from 2 nodes, whatever 2 nodes that I pick out of that cluster are inherently going to overlap, and then I'm going to see the written key, right? So in this case, this node is being written to x equals 5. This guy is being written to x equals 5. Maybe the previous value of x was 3, right, as is shown in this old node that we didn't write to. But when we read, we have to pick 2 of them. So in this case, we're going to pick the write nodes over here. And so actually, every single time that you make a write, you can take a version number for that key and increment it. So if x equals 3 was version 1, x equals 5 is going to be version 2, x equals 5 is going to be version 2. And then when this guy over here performs a read, you're going to see that x equals 5 is version 2 of that key, x equals 3 is version 1 of that key, and so we're going to say, oh, well, clearly this is x equals 5, right? X equals 3 was an old value that we just don't happen to have gotten the proper new value for on that particular node that I read from. Cool, so you may think to yourself, oh, well, this is strongly consistent. There's no way that I can perform a write and someone else can read from that same cluster and not see my write. Now, you're correct. However, there are edge cases with quorums that make them very imperfect. So for starters, let's look at the scenario when a write fails. We can't always roll it back, right? So again, I have all of the sequence numbers written down. Step 1 is that this guy is going to say, hey, I'm client A over here. I'm grabbing the lock. So now this node is going to say, okay, I agree that A has the lock. Now what's going to happen in step 2, it also wants to write to this guy over here, right? Because this is a cluster of size 3. A quorum, we are going to need to write to 2 places in this case. And so our second write, unfortunately, is going to fail. So this does not work. As you can see, I have my x here. So this guy, this node, is going to stay as null for the lock value. So that's going to be a problem. And A realizes, hey, I don't have the lock. So it's aware of that because it didn't get 2 success messages from the 2 clients that it wrote to. Now B comes along and it's going to do the following. It's going to say, I want to grab the lock also. Does anyone actually have the lock? Let me go ahead and check. Well, the first thing that it's going to do is go over to these 2 nodes over here because it got unlucky, and these are the 2 that it happens to be reading from, and it's going to see that one of them is telling it that A has the lock, and now all of a sudden it thinks that the lock is taken when it isn't actually in reality. So that is going to be a problem. So in this situation, B is going to incorrectly read that A has the lock. Now you might say to yourself, well, Jordan, why is it that when A realizes that this write didn't go through, it just goes ahead and reverts this guy over here, right? It can reach back out to that node and undo the write. Well, a large percentage of the time it probably can, but if the reason only one of these writes went through is because the client itself went down rather than due to some network partition over here, how's it going to be revert the write if it itself is down? So yeah, that's going to be a problem. And again, if we wanted to do anything more than that, these guys would have to communicate with one another to realize to revert writes. The point is, you can't rely on asynchronous communication over the network. Once something is written, there's no guaranteed way to make sure that we revert it, and as a result, we can have all sorts of data consistency issues. Another problem with quorums is that they are not linearizable. What does linearizable mean? It effectively means that we can create one cohesive ordering of all of the writes in our system when we actually look at them over time. So here's an example where they're not going to be linearizable. And keep in mind, they have to be linearizable basically in the moment, right? During a write, I have to know exactly what came before something else, because that way I can assign something like a fencing token to it so that I know for a given grab of the lock, which person came earlier and which person came later. So let's imagine the following scenario. We've got a quorum where a cluster of n equals 3. We want to write to 2 nodes, and we want to read from 2 nodes. So client A is going to go ahead and write to these 2 nodes on the left, and it's going to get the fencing token of 1 because they have yet to see any writes. So in this case, I'm assuming that the fencing token that you get assigned is basically the version number that both of those nodes see, and then if you get 2 different version numbers from the nodes that you're getting, you'll just take the max of the 2. Cool, so since this is write number 1, basically we're going to see A is version 1, A is version 1. Now let's imagine that A does what it needs to do and it gives up the lock. So client B comes along and it wants to grab the lock. And now it's writing to these guys. So over here we've got B is equal to version 1 because this guy has seen no writes. And then we've got B is equal to version 2. Now it can compare the two responses that it got back from these nodes on successful writes and say, okay, 2 is clearly higher, so let's say I have fencing token 2. The next thing that's going to happen is C comes along because B has now given up the lock. And now C is going to say, okay, well, here I've got C with version number 2, and over here I've got C with version number 2. It looks like my fencing token is number 2. That's a problem right there because it means that within our system, we can't instantly tell which write came first between C and B because they both have fencing token number 2. So if they now both try and write to S3 at the same time, right, let's say B ended up actually having a process pause due to a garbage collection, so it went down, and now all of a sudden it's writing to S3 with token 2. They're both writing to S3 with token 2. We've got a corruption issue, and things are going to fail. Now, I'm sure at least one of you is going to argue with me in the comments about this, and so I make this very, very small note on it, which I'll cover for about 30 seconds before I confuse myself too much, because you can think about this for literally an hour. If every single node decided to only accept writes with version vectors that were up to date with the current state on that node, maybe we can ensure that we basically, make all of our writes linearizable, right? Because then every write is up to date, and so we can explicitly say that one write is after another. However, what's going to happen then is that every single one of these nodes is going to have to reject quite a few more writes, therefore leading to partial failures. Anyway, major tangent. Don't worry if you don't understand that one that much, but you're welcome to think about that sentence as long as you want. Cool. Now let's talk about distributed consensus, because ultimately this is what we need to build linearizable writes. So what is good about distributed consensus algorithms? Well, unlike something like completely synchronous replication, which does technically lead to consensus but has no fault tolerance, distributed consensus algorithms are fault tolerant. And they allow us to build out linearizable storage, which means we can quickly figure out the ordering of people grabbing the lock, which is huge for us. So as far as writes go through, I'm going to basically quickly go over the raft algorithm again, which we've gone over multiple times, but this is hopefully going to take me sub 5 minutes to do. So let's imagine we're writing to our distributed consensus system. Typically what we'll have is a leader, we'll have some followers, right? Typically we'll have like 3 or 5 total nodes in this cluster. And so what our leader will do is it'll propose the write to its followers, and if it gets basically a two-phase commit to both of those followers, and if a majority of total nodes in the system approve this write, the leader will commit it, right? So it really only needs to hear back from this guy over here, and even if the write to this guy fails, it doesn't matter because it has 2/3 approval, or majority approval in this case, and as a result we can commit the write. So we're going to commit the write over to our leader, so now there are 101 entries in the log, and same and this follower over here, there's 101 entries in the log, and this guy who might be a little bit behind because it's down, it can't progress, but that's okay for the time being. Cool. Step number 2 is that another nice aspect of writes in our distributed consensus algorithm is that writes will actually backfill nodes that are behind. What does that mean? So let's say we've got some leader, again, and 2 followers on the right over here, and this follower is completely up to date with the leader, and this follower is behind. If the leader goes ahead and sends a proposal for a write to this follower, this guy will actually reject that proposal until the leader begins to actually send more old entries. So at first we're going to say, okay, I'm sending you entry 101. This guy is going to say no. We'll then say, oh, well, I'm sending you 100 and 101 now. It's still going to say no. Then it's going to say, okay, well, what about 99, 100, and 101? And then now this guy will say, yes, please send those to me during the actual 2-phase commit phase, and then you'll get the approval there, so we'll backfill you. So what does that actually mean? This gives us a pretty nice property right here. What it means is that if we have a couple of followers, right, A and B, let's say this guy is A, this guy is B, and A has more entries than B does in this particular epoch, right, so that an epoch would basically be for this leader while this leader was the leader. If A has more entries in its log than B does, it means that A contains all of the writes that B does. Because it means that if A has any additional entries, the only way that it could have gotten those additional entries was if it also backfilled all of the previous entries. So we know that having more entries for a particular epoch of a leader means that you are literally, you have the same exact log as all of the other followers, except a little bit more, maybe 1 or 2 entries more. Cool. So that brings us basically to the final step here, which is actually what happens when a leader goes down, because of course, this is hardware and it is prone to failure. So if a leader goes down, the followers are going to notice. They're basically all heartbeating one another, or they're all sending heartbeats back and forth to the leader on an occasional timeout. And basically, some of them are going to notice that the leader might be down. You can send these heartbeats at a slightly differing interval so that we don't have all of them noticing at the exact same time. Cool. So what's going to happen when a follower notices that the leader is down is it is going to become a candidate node, and it's going to do so with epoch +1. So it's going to take the current leader's epoch number, add 1 to it, and say, I'm a candidate for this next epoch. So let's say we've got a leader over here, epoch 10, and there are 100 entries in its log for that epoch. Over here, this guy, all of a sudden, after sending heartbeats and noticing that they cut out, says, I think the leader's down. I'm now a candidate for epoch 11. And by the way, I have 99 entries in my log for this epoch. So what's going to happen now? It's basically going to send that out to all of the other followers, and all of the other followers are going to vote on whether it should become the leader. Now the criteria for voting is pretty simple. It basically just says, in the last epoch, note this candidate had 99 entries, I'll vote for you if you had the same amount of entries or more than me. So this guy, who also had 99 entries, will say, yes, I approve of you as a leader. These 2 guys, on the other hand, who both had 100 entries, will say, ooh, sorry about that, bud. No, I'm not voting for you. And they're both going to vote X. Now, to become the leader, you actually need approval from a majority of nodes. So in this case, this guy would have needed 3 yes votes, but he actually only got 2. So he's not going to be a leader. One of these guys over here will have to eventually become a candidate. And because they have 100 entries in their log, they will get approval votes from all of the other followers. So the main idea here is that because of the fact that one of the followers becomes a candidate with basically one of the more up-to-date logs, right? Such an up-to-date log that it's more up-to-date than a majority of nodes in the cluster, that actually means that it contains all the committed writes from the previous epoch. Because all of the committed writes have gone to at least a majority of nodes in the cluster, and also keep in mind that we're backfilling them as well. So whatever the last write of that epoch must have backfilled at least a majority of nodes in the cluster, and so there should be at least one node that has this criteria satisfied. Cool. Again, I'm going over this pretty quickly, which is why I keep stuttering. You can watch the Raft videos where it should hopefully be a little bit more clear, but the idea is basically, whatever the last write that the leader did before it went down, it must have gone to a majority of the nodes, and that must mean that a majority of the nodes were now equally as up-to-date as the leader, which now means that one of those majority nodes can easily become the leader for the next epoch. That would be how I would summarize it. So what does this look like in practice, right? We have our consensus system over here with 3 different nodes. How do we make a distributed lock out of this? Well, it's pretty simple. You're just proposing writes from the leader, and then those writes go to the followers, and then once they're approved, you can report back to the client that they've gotten their distributed lock. So we've got client A over here, which will say grab lock. Okay, the leader is going to receive that message, do its 2-phase commit over to its 2 followers. It's going to receive approval, and now that gets added over here into the distributed log. So once we store all of that on disk, what we can also do to speed up reads a little bit is actually store the state of all the locks in a hash map in memory as well, which basically corresponds to what was in the log that we're distributing. And then as a result, when we make reads, we can just read from memory as opposed to having to build that state all back up from the distributed log. So it should be relatively quick. Cool. Let's quickly talk about some other implementation details. So for starters, one thing that we don't want is a bunch of clients just constantly polling our distributed locking system and say, hey, is the lock available yet? Is it available yet? Is it available yet? That would be bad because it's going to add a bunch of unnecessary load. We want to keep this thing fast. We want to use it for a lot of different servers at once. So what we should instead be doing is using something like a server-side push, right? We want to keep track of all the nodes that are waiting on a particular lock, and when it becomes available, we can actually go ahead and alert them that the lock has become available. Now there is one trick to note here, which is that if we notify all of them at once, we're going to get a thundering herd. See the following diagram below. In step 1, this guy grabs the lock. In step 2, he releases the lock. In step 3, we convey to all 3 of these other guys that the lock is available, and all of a sudden now they're all trying to grab it at the same time, and we've put a bunch of unnecessary load on our system that we don't need to put there. So how do we solve a problem like this? We can actually just use a queue lock. So the way that we would do that is every single person who tries to grab a lock, we can actually just put them in a queue for that specific lock, such that when the current person who owns the lock releases it, we basically pop them from the queue, we look at the next person who is next up in the queue, and we alert them via either a long poll or a WebSocket or a server-side event that they are ready to go. So ultimately, that should keep things looking good. Of course, once you actually do possess the lock, you want to constantly be sending heartbeats over to the distributed locking server so that we can make sure that if we think you're down, that we time out the lock and give it to the next person in line. And so we can do that by basically just using a WebSocket, right? Because the nice thing about a WebSocket here is that it's going to allow us to send all of those pings via a heartbeat without sending repeat HTTP headers over and over again, which may actually make this go a little bit faster and use a little bit less load on our networking capabilities. So I do write over here that in theory we could have done something like a long poll request every time we request for the lock. However, it does feel like a WebSocket may be good enough anyway, because eventually when you do get access to that lock, you're going to have to be sending those heartbeats over it. Cool. The last piece of this puzzle is actually going to be our diagram. So in step 1, we've got client A over here trying to go ahead and establish a WebSocket connection with our distributed locking server. This is going to be the leader. And then over here we have a follower and another follower. Whenever the leader receives such a request, it's going to perform its two-phase commit over to the followers, but again, it only actually needs one out of those 2 followers to respond, hence we do have a little bit of fault tolerance. The bigger that we expand this cluster, the slower things become, but at the same time, the more fault tolerance that we afford ourselves. Okay, so we can go ahead and establish our WebSocket connection, and since this is the first one being made, we're going to receive a fencing token of, let's say, 20. This guy might do the same thing over here, client B. However, client A still has the lock. So client B is going to be behind client A in the queue. Eventually, client A is going to go back over the WebSocket and say, hey, I'm unlocking now, I'm good to go. This guy gets removed from the queue. B is told via the WebSocket connection that it has token 21, and now it can go ahead and write over in S3. If for whatever reason A was to try and write again with its old token 20, that should be rejected, because of the fact that it is smaller than 21. Well guys, I hope this all made sense. Again, just a big synthesis of single leader replication, leaderless replication, distributed consensus, thundering herd problems, some real-time alerting frameworks, and yeah, hopefully it made for a semi-cohesive video. Anyways, I've got to head off. Thank you again for the big subscriber milestone. I really appreciate all of you, and I will see you in the next one.